Assalamu alaikum students. We are going to perform some example problems on Fourier transform, continuous time Fourier transform. In this example, we have to find out Fourier transform of one-sided exponential signal. The expression is given xt is equal to exponential minus alpha t times ut. Here ut is unit step function, and this is how a one-sided exponential function looks like. It exists only on the positive side because it is multiplied with the unit step function. It confines it towards one side because unit step function also starts from 0 and goes to positive infinity, and its magnitude is 1. So when it multiplies with the exponential signal, it keeps it towards the positive side only, and all the terms on the negative side means from 0 until minus infinity, they all reduce to 0. Okay, when we perform Fourier transform, the standard procedure or the standard formula is that we multiply our function xt with exponential minus j omega t and perform integration from minus infinity to positive infinity. We can write it like this here, but since it is one-sided function, our limits of the integral will change. They will become 0 to positive infinity. Okay, and after performing the integration on this exponential function, we get this value. Okay, and now we apply the limits 0 to infinity, we get this value. This is our Fourier transform of the one-sided exponential signal. Okay, now we have to perform Fourier transform on two-sided exponential signal. Now you notice that the function is the same, exactly the same. Only one thing is missing, that is the unit step function. It is missing, it's not here now. Now it will look like this. So the exponential is the two-sided exponential function exists on both sides of 0, positive side and negative sides both. Okay, now we'll do exactly the same thing. We will multiply this function with exponential minus j omega t, and then we split it into two halves, minus infinity to 0 and 0 to positive infinity. Okay, because actual integral is from minus infinity to positive infinity, we can split it into two, minus infinity to 0 and 0 to infinity. Now we perform integration as usual, each part separately, and we get this value. Now we solve it and we can get 2 alpha over alpha square plus omega square, and this is the Fourier transform of two-sided exponential function. Okay, in this example, this is an exercise for you. You have to do it yourself. You have to show that the Fourier transform of the unit step function is pi times delta omega plus 1 over j omega. This is an exercise for you. You know what is a unit step function? Its definition is written in the lower right corner. You can see that, and then you follow the same steps as we did in the previous two examples and try to get this expression as Fourier transform of unit step function. If you face any problem, you can discuss with me and I will share the solution with you. Here are some of the famous functions and their Fourier transform. The first one on the left column is the function and right column is their Fourier transformation. So the Fourier transform of number 1 is 2 pi delta omega, and the Fourier transform of unit step function that you have to do yourself is equal to pi delta omega plus 1 over j omega. This is what you have to show. This was your exercise. And the Fourier transform of delta function is 1, and similarly if you go down to sine and cos, and all of them are given to you. These are the ones which are more commonly used, and then at number 15 and number 18, these are the ones that we are going to use in our next example, and we have already found their solutions in previous two examples. Then number 15 is one-sided exponential function, and number 18 is two-sided exponential function. Okay, so in this example, determine the output signal yn of an LTI system using Fourier transform of the impulse response of ht is equal to exponential minus a or alpha t times ut. This is the one-sided exponential function, which is actually in this case is the impulse response of an LTI system, and the input signal is unit step function. Okay, now you know that the output of an LTI system is equal to the convolution of impulse response and the input. Therefore our and the convolution in frequency domain is actually the multiplication, right? Therefore we can write our output in frequency domain like this, that output is yn. In frequency domain it will be represented with capital Y, and omega represents the frequency, so it is in frequency domain at the moment. So in frequency domain it is a product of the Fourier transforms of unit step function or input and the impulse response of this system. So this F italic styled F represents the Fourier transformation of the signal which is in the brackets. So Fourier transform of unit step function times or multiplication with Fourier transformation of one-sided unit step function, which is actually the impulse response of an LTI system for this example. Okay, now we have to perform Fourier transformations on both of these, but since we already know what is the transformation, what is the result of that, as we did in our example number 1, where we found the Fourier transformation of one-sided exponential function, and the one that I gave you as exercise for unit step function, we can directly write their values here. So the Fourier transform of unit step function is pi delta omega plus 1 over j omega, and the Fourier transformation of exponential minus alpha t times ut, which is one-sided exponential function, its Fourier transform is 1 over alpha or a plus j omega. Now we do this perform the multiplication and we rearrange our terms, we get this form. So here the reason for bringing it into this form was will be clear to you just now. Here this term is actually, as you know, is the Fourier transform of what? Unit step function. You can see its first step. This was the Fourier transform of unit step function, right? So this is actually the Fourier transform of unit step function. So when we perform inverse Fourier transform, we will get unit step function back. Means that when we perform Fourier transform on unit step function, we get this formula, pi delta omega plus j omega, or 1 over j omega. And when we perform inverse Fourier transform on this formula, we get our unit step function back. Okay, so this was the reason to bring it into this form, so that we can easily perform inverse Fourier transformations. Okay, and the second one, this is the Fourier transform of one-sided exponential function, right? So means when we apply inverse Fourier transform on this, we get our one-sided exponential function back. Okay, so why we needed to perform inverse Fourier transform? Because we want the output signal in not in the frequency domain but in the time domain. So because it was easier for us to perform convolution in frequency domain, because it is simply multiplication, that is why we are doing it in frequency domain. But in order to go back to time domain, once we have solved our convolution by multiplication in frequency domain, as now here we have completed the convolution in Fourier in frequency domain. Now we have to bring it back to time domain, and to bring it back to time domain we have to perform inverse Fourier transformation. So by performing inverse Fourier transform, we will get 1 over a ut minus 1 over a exponential of minus alpha t times ut, like this. Okay, so this is after performing inverse Fourier transformation. We will replace the terms with the inverse Fourier transformed term. So capital Y omega will be changed back to yt, means in time domain now, after performance of inverse Fourier transformation, and our final result will look like this. So that's all for now. If you have any question, we can discuss later on.